welcome back. In our last video, we successfully built our CUDA histograms, but we ran into a massive performance wall. To be more specific, we are forcing the millions of threads to use the atomic add here. They will directly add this access to these 7 bins in global memory, and we created a catastrophic traffic jams at the L2 cache. Okay. Today, we are going to try to eliminate this bottleneck. We're going to make our kernel maybe 5 or 10 times faster using one of the most elegant design patterns in parallel computing, the shared memory privatization. Okay. To understand the privatization, think of a national election in the United States. Our previous global memory approach was like forcing 16 million citizens to fly to the capital city and drop their ballots into just 7 national the boxes, right? The lines were endless there. Privatization changed the rule. Instead of flying to the capital, we divide the voters into local villages. These are our strat blocks. Inside every village hall, we set up 7 private local boxes. The citizens vote locally and instantly. When the village is done counting, the village administrators takes these 7 summarized numbers and flies to the capital to update the national boxes. I think this is a good example. Basically, we reduce millions of national trips down to just a handful. Okay, let's look at how we code in the CUDA side. So the codes are within the shared memory atomic directory, and you will see it here. Okay, see it here. Okay, let's see our kernel directly, because all other things I would say it's pretty it's pretty same, right? Okay, let's directly see our kernel histograms. First, we declare some shared memories. Okay, as results, and its size is 7. So basically, we allocate an array of 7 integers directly inside this streaming multiprocessor. Right, it's in the L1 cache. So every single thread block gets its own independent physical copy of this array s underscore result. Yeah. But before do that, please pay attention. We have to kind of clean, or we have to initialize the shared memory thread to 0. Yeah. So we use a if condition here. We do not use a for loop. Yeah. Because we use a if condition, then the first 7 threads of the block, okay, can simultaneously, right, set this value to be 0. It's in perfect parallel. Okay. It's a tiny detail, but it shows a good way to write the parallel efficient code, right? Next, come to the matter of our death. So after we initialize 0 for the shared memory as readout, and we need to synchronize all the threads. Okay, yeah. If we do not, then some kind of thread might already counting letters and write to the shared memory before thread 0 has finished clean out the garbages. So that's not good. So we have to synchronize all threads. Once all threads is synchronized, we enter the great stride loop, right? Inside the loop, we still use the atomic add, but you see here, but for the atomic add here, we're no longer attacking the global memory, right? We're no longer attacking the global memory. We're doing atomic additions on our local S result, right? Because this happens in the shared memory, the cost of the atomic correlation is almost zero. Right. Okay. Yeah. So this for loop is pretty important. Yeah. Okay. So we have covered the grid stride loop in the previous videos. After the loop finishes, the local counting is done, and we need to our second barriers sync threads. We must wait for every single citizen in the village to finish voting. Right. Finally, if it's time for the village administrators to report the capital. So if this thread IDX is less than beans, what does that mean? You have to copy the results from the shared memory to the global memory, right? To the global memory. Okay. We can do a maybe we can do a quick math here. Let me put here. So let's see, we have 16 million 16 million letters, okay, and let's see, we have 1000 thread blocks, and then we just reduce our global memory atomic correlation from 16 million down to 100 times 7, right, down to 7,000. So we eliminate maybe 99% of the global kind of log contentions. So that's very huge. Okay, that's very huge. Yeah, I will compile and run the results later. But before that, let's do a small variant here. So if you scroll down to the code, you'll find we assign the number of blocks is exactly same as n divided by the thread per blocks. Okay, but since we let's see, since we use the grid stripe loop, actually we can launch less threads, right? And let each thread to do more work within the block, right? Okay, let's see, if I divided this by 4, what does that mean? So that means for a thread within one block, they have to loop 4 times before it finishes work, right? Then that brings us some benefits, because we how to see, because we launch small number of thread of blocks, right? Then we have less contentions, right? Think about it. Yeah, I'm trying also to organize my thoughts and my mind. Think about it. So if we divided this by 4, okay, we have small number of blocks, and then within each block, right, there will be less contentions compared with the previous large number of blocks, right? So that's something I will also experiment uh, in the compiling and running stage. Okay, let's do it. So here, let's clean everything. Okay, so first let's go to the global atomic example, the previous example here, right? You can compile it exactly same command lines as in previous video. You just compile it, and then you can run it. We use the insight system to do the profiling. Okay, so you can ignore all other numbers, but just focus on the kernel running time. Yeah, it's here. Okay, it's around I would say 7 million nanosecond, right? 7 million nanosecond. Remember this number. Then we go to the shared memory. Okay. We go to the shared memory, and we can compile it. But pay attention is now we still use the block is n divided by the number of threads. Okay, that's our first try. Okay, come on. See here, that's huge, right? 7 million. Okay, 170k nanosecond. That's huge. How many? 7 million ones. It's about maybe 40. Yeah, around 40, right? Around 40. 40 times speed up. Okay. Yeah. What if we use small number of blocks, but let the threads do more work? Divide by 4. Okay. Let's recompile it. See here, around 95 key nanosecond. It's about twice speed up, right? So you'll find it's really amazing to optimize the CUDA code in different aspects, right? So, but the lessons we learned here is that we have to use shared memory parallelizations instead of using our global atomic operations. And we can also let the threads do more work and reduce the number of the blocks in our problem. I hope you enjoy this video and see you in the next video.